Hey everyone, welcome back to the data science interview question series. In this video, we will be looking at why the sigmoid function is used in logistic regression. But before I tell you the answer, I would like you to hit the pause button and think about the solution. Okay, before we jump onto the solution, I would request you to hit the subscribe button and press the bell icon so that you never miss an update for an interesting interview question. Let's start off by defining the objective function of the logistic regression. In order to find the best plane, we need to maximize the sum of sine distance of all the points. But what is sine distance? Let's try to define the sine distance in the first place. So I have a couple of points x1 and x2, and I have a plane which divides both of them, whose normal to the plane is w. So for the sake of simplicity, the distance from both of the points to the plane is d, and the d will be positive when the point lies in the same direction of w, and d will be negative when the point lies in the opposite direction of w. Labels could be both positive and negative. Here I have two positive labels, but I could have another point, say x3, which has negative label. So the sine distance becomes the multiplication of label with the distance from the plane. Now let's consider a couple of more points, x1, x2, x3 and x4, and w, which is normal to the hyperplane. For the sake of simplicity, the green arrow represents the magnitude of one unit, which means all the 4 points are equidistant from the plane. Now let's calculate sine distance for all of the points. The first two ones represents the labels for x1 and x2, which are the positive labels and their respective distance. These are the labels for x3 and x4 and their respective distance. Here the distance is negative since both points x3 and x4 lies on the opposite direction of w. Now we sum them up and the value we get is 4. Suddenly an outlier point comes in, which is x7, whose distance from the plane is 50. Now we have to add this distance also into the sum of sine distance. So the distance is going to be positive here because the x7 lies in the same direction. It has negative label. So the sum becomes minus 46. Now let's evaluate how well the hyperplane was able to separate both all the points. Now let's evaluate how well the hyperplane was able to separate out both of the classes. So x1, x2, x3 and x4 are correctly classified while x7 was misclassified. So 4 out of 5 points are correctly classified. So the accuracy becomes 4 upon 5. Distance is pretty low. Can we do something better to improve the sine distance? How about if we turn the hyperplane to 90° and then the plane would be much more closer to x7 than it is right now. After rotating, this would look something like this, and I'm defining this hyperplane as W1. Again, here the green arrow represents the magnitude of 1 unit. And let's calculate the sine distance for all the x values again. So the distance of x1 and x4 are going to be 2 since they are 2 green arrows away from the plane, and the distance for x2 and x3 is going to be 1, and these are their respective labels. Now also add the distance of x7, which is 1 over here. So the final value is 1, which is better than minus 44. Does this mean that W1 is really better than W? Let's evaluate it. Here we have x1, x2 and x7 which are correctly classified, but x4 and x3 are classified as positive labels, but in reality they are negative labels. So here there are two misclassifications. So the accuracy becomes 3 out of 5. But therefore, we actually cannot use W1 even with the better sine distance. This is where the sigmoid function comes to the rescue. Sigmoid has the nice property to squash the values between 0 and 1. This is how the graph of sigmoid looks like. For the value of x greater than 4, y value saturates to 1, and for the value of x smaller than -4, the value of y saturates to 0. This property will help in reducing the impact of outliers. Now let's apply the sigmoid function to the sine distances. So onto the normal W, before applying the sigmoid function, the sine distance was -46. And here the z will represent the sigmoid function. So now we will apply the sigmoid function to the sine distance. Specifically to the outlier value, if we apply the sigmoid function, the value will be squashed down to 1. And for the z of 1, it is going to be 0.73. Now we'll add all of them, and the final value is going to be 1.92. And as we know, there are 4 correct classification and 1 misclassification. The accuracy is 4/5. But what about the vertical plane with sigmoid? This is how the vertical plane looks like, where W1 is the normal to the hyperplane. And before applying the sigmoid function to the sine distance, the value was 1. And after we apply the sigmoid function, we calculate z of 1, which is 0.73, and z of 2, which is 0.88. And then we add up all of the sine distance. The final value we receive is 0.73. And as we already calculated, the accuracy for this plane is going to be 3/5, since x1, x2, and x7 are correctly classified and x4 and x3 are misclassified. So here the sine distance of W plane is greater than W1. Also the accuracy of W is greater than W1. So we can safely say that W is really better than W1. And applying the sigmoid function to the sine distance makes it more robust to the outliers. Now let's summarize all the points that we have seen up until now. Sigmoid squashes the value between 0 and 1. Just using sine distance can lead to suboptimal hyperplane in case of outliers. Sigmoid diminishes the impact of outliers to a larger extent, which helps in finding the optimal hyperplane. Last but not the least, sigmoid output has a nice probabilistic interpretation, which means its output can be treated as probability values. If you find this video helpful, please consider subscribing. Also push the bell notification so that you never miss an update for an interesting interview question. Who knows, this might be your next interview question. Also, if you have any suggestions for other topics, please let me know in the comment section, and I'll see you in the next video.